Now in this section, we'll look at the cumulative distribution function. And the cumulative distribution function, or CDF, is really just a way to describe a probability again. It's just another distribution function. So we can look at a cumulative distribution function, and our notation for that is going to be a capital F of a random variable x at a specific value little x. So again, capital F's are different than what we've had before. A lowercase f is going to be a probability density function, or PDF, that we just got through looking at. And a capital F is a cumulative distribution function. And a cumulative distribution function is just saying what is the probability that our random variable x is less than or equal to some arbitrarily selected value little x. So to look at this in a little bit more detail, that's going to be for continuous random variables. It's the integral from minus infinity all the way up to that x that we select of the probability density function, f of x, integrated over dt in this case. This internal variable is kind of arbitrary because it's going to integrate out, but we'll just say f of x at t integrated over dt. So with that, we can kind of look at this as a little bit of a piecewise thing and build out what a cumulative distribution function could look like. And before we do that, though, one little side note is that cumulative distribution functions work for both discrete and continuous random variables. In this case, we'll look at it primarily as a continuous random variable, but we will look at a quick discrete example as well just to give you some information about it. But this is one of those distributions that can work for both discrete and continuous random variables, both. Now, jumping right back in, let's say that we pick some x sub 1 as a point on our line right here, and we'll call that x sub 1. And let's say that we're interested in the probability, again, that the random variable is less than or equal to that x that we've selected, in this case, x sub 1. Well, for this point right here, we can say that this x sub 1, there's nothing going on over here. All of my probability density is in this gray shaded box here. So the probability that the random variable is less than that x sub 1, so this entire area over here, is just 0. So on a cumulative distribution function, as long as x sub 1 is less than this point a here, we can say that the cumulative distribution function, the probability that our random variable could be less than our selected point, is 0. So we can actually draw that in right here as our cumulative distribution function and say that it's 0 anytime that x is less than a. Now, as we progress through this gray box here, let's say we pick another point, x sub 2, and x sub 2 will be inside the gray box. Now, to find the area of this, let's say that we're interested in our shaded area. We know the height, because this is a uniform distribution, is just 1 over b minus a. That's the height of a uniform probability density function, or a uniform PDF is just 1 over b minus a. Now, the width is x sub 2 minus a. So that's x sub 2 minus a. And we're going to multiply that by 1 over b minus a, which means that we're really dividing by b minus a. And that is our PDF, or our probability density function, for any selected value when we're interested in looking at what's to the left, what's less than that x sub 2. So with that, we can go through and say, hey, as x sub 2 increases, as this gets larger, we know that our result is going to get larger. So we can draw this graph as increasing up to our point B. And at some point B here, we know that it's going to do something. But let's figure out what that is. If we look over here past B, this is x sub 3, we know that we've already encountered all of the area that is described by this uniform PDF. We've covered everything once we get past B, and we know that the sum of a PDF is equal to 1. So the probability, if we're at x sub 3, that the random variable x is less than that has to be equal to 1, because over here it's just 0 again to the right of this arbitrary point B that is the top end of our uniform distribution function. So we know that at some point we're just going to hit 1 and we're going to stay there. And so this is a cumulative distribution of 1 where we can say that for all values of x that are greater than the maximum value of our uniform distribution, this B, the probability that we're less than that is just 1. So this is a very graphical approach to it. It's kind of a little bit of hand wavy, but it gives you a good idea of how a cumulative distribution function works. It basically says if I wanted to know for any arbitrary point, let's say that x sub 4 right here is the point that I'm interested in, I can just go straight down to my cumulative distribution function and find out what this value is. Whatever that value is in my cumulative distribution function is the probability that x is less than that value. And we'll see a lot of applications where this is going to be useful. But before we do that, let's go ahead and clean up this graph a little bit and talk about some of the advantages of cumulative distribution functions. So as you may recall, we said that this cumulative distribution function, the capital F sub x for the random variable x, is equal to the probability that the random variable is less than some value x. And we said that that is the integral from minus infinity to x all the way up to whatever point we've selected of the probability density function. So one of the things that we can do if we do some quick math, and we'll skip the proof on this just for the sake of time, but if we do some quick math, we can find that ultimately the derivative of our CDF, of our cumulative distribution function, with respect to our x, is equal to the probability density function. So up here we've actually said that the cumulative distribution function is equal to the integral of our probability density function. And the same is true the other way around, that the derivative of our cumulative distribution function is equal to the probability density function. Now there's a little bit of a gray area here as you reach these points that aren't well defined where the derivative is different whether you're approaching from the left or from the right. In this case, there's some positive slope as you're walking from right to left. It's positive going left to right. And then in this case, there's zero slope and you have a disjoint point right there where the derivative is different depending on which direction you approach from. This equation doesn't hold up in those situations. But for any portion of a cumulative distribution function that's well defined, that's not piecewise, we can find the probability density function just by taking the derivative of our cumulative density function. Now, the other important thing here is that because of that, once we have our CDF defined, again, as long as it's cleanly defined, we have all the information about any random variable that we need because we can get our probability density function out of the cumulative distribution function. And so just some cool little tips and tricks there. We're not going to work any examples on that yet, but we will come back next week and work a couple examples on how to work those two back and forth. Now, I mentioned that a cumulative distribution function also applies to discrete random variables, and this is kind of what that equation looks like. Again, it's still just going to be a capital F, so the same notation for the cumulative distribution function, and it's the same premise that we're looking for the probability that the random variable is less than or equal to some specific outcome. But where things get different is we're going to look at the sum as opposed to the integral. Again, we said that discrete random variables tend to use sums and continuous random variables use integrals. But in this case, we're looking for the sum of all values of k, where k is less than or equal to the value of x that we've selected. And then we're going to sum our probability mass function, our PMF, of the random variable x for all of those k's. So if we draw this out, what we can do is say that for any period less than this 1 here, and these graphs are stacked vertically, so on the top we'll have the probability mass function, on the bottom we'll have the cumulative distribution function. But these graphs are stacked vertically, so we can come in and say that for anything less than 1, we have a cumulative distribution of 0 because we've not reached any of our outcomes for our probability mass function yet. But as soon as we reach our probability mass function of 1, we see that this has a mass of 1 over 4, or 1/4. So our cumulative distribution function is going to have a stair step to it. And this value right here is going to be 1 over 4. Now, we can keep moving, and this will just keep progressing all the way up until we have our next probability mass at 3, which is 1/2. And so at 1/2, we'll step again, and this is now 3/4. And again, that's just the 1/4 plus 1/2. And then that will step to 4, at which point we'll experience another step because of this 1/4, and we'll arrive at our end value of 1, our cumulative distribution 1. Now, this is a really quick and easy way to look at a probability mass function, and in general, you'll see this type of behavior. A cumulative distribution function is going to be maybe a little bit more rounded, a little more smooth, whereas a cumulative distribution function for a discrete random variable is going to follow this stair-step pattern, where every time you encounter one of the possible outcomes for your probability mass function, you're going to have this vertical line as you step to your next outcome. Now, a couple general properties of cumulative distribution functions that we'll look at. The first one is that every cumulative distribution function we said is just equal to the probability that our random variable is less than or equal to this argument to the cumulative distribution function. Now, because of that, we're always looking less than or equal to, and since we can't have negative probabilities, cumulative distribution functions are always non-decreasing. They either stay flat or they increase, but they can never decrease. That, again, since we can't have a negative probability density or probability mass, cumulative distribution functions must always either increase or stay flat. They cannot decrease. Now, the other thing is that the cumulative distribution function will always approach a value of 1 as our x approaches infinity. Now, as we reach our far right edge of some cumulative distribution function, and let's say that this right here is our 1, we know that as x increases, we are getting closer and closer to 1. Likewise, as x decreases, as x goes to negative infinity, the cumulative distribution function will tend towards 0. And this makes sense because it's cumulative. The closer you get to negative infinity, the less probability you have of being there. And the closer you get to positive infinity, the more likely it is that you've covered every possible value of the random variable x.